Okay, so I think we can go ahead and get started with the M-Cubed seminar. I'm pleased to present Dr. Zachary Lebo. He received BS degrees in meteorology and mathematics, as well as an MS in meteorology from Penn State in 2007, which was followed by his PhD at Caltech in 2012. Then he came here to M-Cubed as an ASP postdoc, some of you might remember him, in 2012 to 2014, and then took a research position at Ceres. Zach transitioned to academia in 2015 when he joined the faculty at the Department of Atmospheric Science at the University of Wyoming, and he's currently associate professor in the School of Meteorology at the University of Oklahoma. Additionally, Zach serves as an editor for Journal of the Atmospheric Sciences and is chair of the AMS Committee on Cloud Physics. Beyond his academic duties, he and his wife have two amazing children, and he is an avid runner with a nearly 11-year running streak. That includes running at 4 o'clock this morning before he caught a plane to arrive here. The floor is yours.
Yeah, so if I fall asleep, that's because I did get up and run at 4 o'clock this morning before leaving for the airport to get here. Appreciate the introduction, Hugh. I finally figured out the last time I was here, it was in this room for a workshop on cloud chambers, which I think was in like 2019 or so, give or take. Yeah, so that was the last time I was here. Excited that I'm able to come back and talk a little bit about research that I've been doing since I was a postdoc here. I've kind of framed this talk around sort of a storyline of research progression that started all the way back when I was doing my PhD, through my time here as an ASP postdoc, and then work that we're still doing on this topic of aerosols and convective clouds. Some of the work that I'll be presenting is done by students. Most of it's done by students, one of which is in the audience today, who came up here with me. No, she's been here for a while working with folks here. Yeah, without further ado, I can get started. I actually put this slide when I made these, put this as I made this little animation, and then like the day after I made this, we had this really awesome supercell. This is late September. We had this supercell in Norman that I could not take pictures of that dumped some two-inch hail in Oklahoma City. Why is it here? These are the types of storms we're interested in studying, in particular how aerosols could influence these and what that magnitude might be. So why would we care about, or why would we actually study these clouds? I have lots of pictures from storms in Norman. It's pretty easy to get them, but why would we care? Severe weather is the main reason. These storms, these clouds are responsible for some of the most severe weather that we experience on Earth. Not going to go into this in a lot of detail. I'm sure you're all aware of this. Tornadoes. Hail is the big thing that's receiving a lot more attention. 2023, the average insured losses per outbreak were over $1 billion, or 1 million. 1 billion? That can't be right. Yes, that's right. Never mind. And then finally, Ice Chip is a new field campaign that has finally been funded and will be occurring next year to actually study this problem. Straight line winds, this is just the example from the Iowa derecho, $7 billion in losses. And then flooding. Recently, the impacts of Helene caused catastrophic flooding due to the torrential downpours and the convective clouds, the convective storms associated with the landfalling hurricane. And so given that these clouds are responsible or associated with some of these extreme weather hazards, and any way in which humans could influence them or influence the strength of these storms is an important topic to study. And one way that's been proposed by which humans could influence these storms, well, there's two main ways that have been discussed. One is warming up the atmosphere and how that influences convective clouds, but also how emissions of aerosols could influence the properties, strength, et cetera, of these clouds. So I hate to show this figure, but I also show it almost all the time because this is kind of where some of the foundational work kind of stems on this topic, was this paper published in Science now 16 years ago. Fun, maybe not fun, but interesting fact, when I started my PhD, I was actually going to be doing climate work. And then I actually went back and looked, and I found the email from my advisor that was sent to me. This was on September 10th, 2008, so a little over 16 years ago. He sent me an email with a link to this paper, and then my PhD shifted significantly to work on this topic right here. The paper goes through a sort of theoretical, hypothetical, conceptual model of how aerosols could influence the properties of convective cloud, the microphysical properties of convective clouds, and how that could feed back on dynamics. The title maybe is a little bit provocative by saying that this could lead to floods or drought. That seems pretty extreme in my opinion. Hopefully by the end of this talk, I'll convince you that that's really actually the case. But this sort of set the stage for some of the subsequent studies that have been conducted now over the last 15 years or so. So how might aerosols, can everyone hear me if I walk away from the microphone? Is that cool? Yeah? Am I loud enough?
People online don't.
I have this on.
Oh, okay.
Yeah.
But they can't see you
They can't see me?
if you walk away.
You're getting the thumbs up from it.
Yeah, we're good? Okay, we're good. Cool. So we put this schematic together in a paper 2011 that illustrates this sort of the aerosol cloud spectrum, if you will, in 2 dimensions. So this x-axis here, I guess I should use the pointer for people online. This x-axis, that's weird. Can I point, or is that?
It's bottom left there.
Yeah, I know, but then people online can't see me. Are we good? Okay. So this axis here is the aerosol spectrum, and then that axis down there is the drop spectrum, and you can think of these dots right here as your unactivated aerosol. They activate, they form drops, collision coalescence, condensation and evaporation. These particles are the building blocks of clouds. And the abundance of those clouds has a direct impact on the number of cloud droplets, and that therefore, then that indirectly will then affect the condensation evaporation rates as well as the collision coalescence rate. These are important because they have impacts on the thermodynamics through warming and cooling, but also collision coalescence affects drop sizes, and that can have an effect on the distribution of mass within clouds. So all of these can have an impact on clouds in general. And in convective clouds, these are important because in the updrafts of these deep convective clouds, we have condensational warming, depositional heating, freezing going on. But then also in the downdrafts, we have cooling through evaporative cooling from rain, as well as melting and as well as sublimation. So these processes could have an impact on these up and downward moving air motions in convective clouds. So a little thought experiment of how this might work, and the point of these slides is to sort of illustrate different mechanisms that have been proposed for how aerosols could have an influence on convective clouds. So everything here on the left is going to be a clean scenario, everything on the right is going to represent a polluted scenario. And then we just essentially are going to lift some air that has clean and polluted conditions. Already established that that has a direct influence on the number of cloud drops. So the clean air has fewer cloud drops. They tend to be larger then, assuming that the liquid water content remains the same. So we have few large drops and a lot of really small drops on the polluted side. And this will then influence the collision coalescence rate. So on the left, more likely to have collisions. On the right, they're less likely, so you don't have a lot of large drops being formed through the process. And this has all been well known now for 50, 60, 70, whatever years. The first indirect and second indirect effects for warm clouds, cloud brightening and precipitation suppression. I'd argue that these are pretty well understood, and we can very straightforwardly represent them in these little schematics. But things get a little bit more complicated in convective clouds, in particular deep convective clouds, where we have more than just liquid. We have ice, we have cold regions, and we also have areas of those clouds that have both ice and liquid. So let's see what happens as we start lifting this air. Before I get to that, I want to talk briefly about what's going on in terms of the thermodynamics at this stage in the warm area, in the warm region of these clouds. So the idea here is that on the right, for various reasons, one in particular, that the quasi-steady state supersaturation is reduced compared to on the left. You have an increase in the bulk condensation. That's an increase in warming. And if you just use this very simple, I don't like putting equations in talks, so I put this very simple thing in words, that'll increase your temperature perturbation, and that's directly proportional to buoyancy. And so you might expect that to have an impact on a positive impact on vertical velocities. We're going to call that the warm invigoration effect. Now we start lifting those parcels of air. One thing that's been proposed in the literature is that because the cloud on the left has these raindrops, they're going to fall out relative to the mostly, oh, I forgot a rain, this guy. One drop fell out, sorry. He must have got missed in the animation. The clean air is the polluted cloud is mostly small drops. They get lifted up. And so the argument that's been made now is that you now have more freezing in the polluted case, and that again has a positive impact on the temperature perturbation and thus buoyancy. And I'm going to call that mixed phase invigoration. There's also the subsequent impact that there's more ice on the right that can deplete the water vapor more readily through deposition, and so that would also have the same impact. However, at the same time, there's more mass in the cloud on the right. On the left, that's precipitated out. So that's going to impact the hydrometeor loading, and that has a negative sign in front of it, so that would actually reduce buoyancy. And that's been called enervation in the recent literature, and especially in a recent paper by Adele Eigel. Right? So beyond those three different impacts there, the two invigorations and then enervation, in a paper that Hugh and I wrote that came out of my postdoc time here, we talked about the influence of aerosol particles on convective cloud microphysics and cold pools, and that was illustrated in this little schematic here, where going left to right is clean to polluted. And the key takeaway here is the red dots, which represent rain. In the simulations that we did, we showed that in the more polluted scenario, you had fewer but larger raindrops, and that had a weakening in the cold pool through reduced evaporation, and that led to these less tilted updrafts. We're going to call those cold pool effects. So we have 4 different effects so far, and just to sort of briefly recap them here. Warm invigoration, this has to do with a changing condensation rate in the warm region below the freezing level that can influence the updrafts. Mixed phase invigoration, this has to do with changes in freezing and deposition aloft that can also have a positive impact on buoyancy. Enervation has the opposite impact. This has to do with hydrometeor loading, which actually would reduce buoyancy or suppress updrafts. Cold pool effects, this has to do with changes in particular with rain size distributions and how that influences the latent heating, the cooling at low levels in the cold pools, and feedbacks on the low level thermodynamics. And then last that I didn't talk about is entrainment. This has been very recent in a paper published just last year in GRL, that the entrainment rate in these clouds is, entrainment influences the ability for aerosols to actually affect the updrafts through these invigoration processes. I'm not going to get into that, but it's just there. If you're interested, you can check out the paper in GRL on that. So that was all kind of hand-wavy. Can we quantify these effects individually? Can we actually tease out how important some of these different mechanisms might be? And so in a paper, I forgot to put it on the reference on here, that also came out of my postdoc time here, as well as when I was at NOAA, I had this idea to place an aerosol perturbation at different levels in the model in simulations of a squall line in WRF. And my idea originally was to look at whether local versus distant air pollution sources may have differing impacts in convective clouds. And what I actually found on it was that it actually allowed me to isolate some of these impacts. It was kind of an accident that came out of it. And so everything going forward here in the next few slides, blue is going to indicate that the polluted air is only at low levels. And when I say low levels, it's below the freezing level. Mid-levels is basically between the freezing level and about 10 kilometers. And then green is all levels, is just add the aerosol everywhere. On the left here, we have profiles of latent heating rates. Red is the warming, blue is cooling, black is the net latent heating rate. These are averaged in time and space. And then the top panel here shows you the situation for the aerosol added everywhere and at low levels. And I put them together, they're essentially the same. There's a different figure in the paper, but more or less the same result. And then the mid-level result is down here. Solid and dashed is clean and polluted. And so when we add the aerosol at the mid-levels, you can see that the clean and polluted profiles are essentially identical. There's very little difference in those two in terms of the bulk heating rate. But when we add the aerosol at low levels, and everywhere, we get this increase in warming as well as cooling at low levels in particular. And so one takeaway from this is that perhaps we can think of the low-level and all-level aerosol perturbations as representing the potential invigoration effect, because the mid-level aerosols aren't really doing anything here in terms of the time and spatially averaged latent heating rates. So then we looked at the cold pool. And so here on the left is showing you the change in this value C over delta U, the vertical integral of negative buoyancy in the cold pool relative to the wind shear. And the wind shear is not changing in these simulations. They're idealized. So any difference here is caused by changes in buoyancy in the cold pool. And so we walk through here. In this case, the value of C over delta U is about 2.6. So following some of the work of people that I aspire to in the audience, a decrease should imply perhaps that there's more optimal conditions for these systems and thus stronger updrafts. And so if we look at the green curve here, when the aerosols are added everywhere, this ratio decreases by anywhere from, well, it's almost zero there, but all the way down to about 15% decrease, which is attributed to a reduction in the evaporation of rain. When the aerosol is added only at low levels, we actually see the opposite or no effect on the cold pool at all. But there was an effect on the warming, at least at low levels, primarily in the updrafts. And then when the aerosol is added at mid-levels, we get almost the same as the aerosol being everywhere. So this suggests perhaps that we can use the mid-level and all-level conditions or simulations to focus on the cold pool effects, because that's the only two cases in which we're seeing a change in the cold pool in these simulations. So what about the updrafts themselves? So this is showing you profiles of the convective updraft mass flux. For each of these cases, this is the relative change. So right of the vertical line indicates that the polluted scenario is giving you a stronger updraft. Left is showing that the clean case is stronger. And so when we have all of these effects combined together in the green, the all levels, we get the green profile on the left, an increase of about 12 to 14%. When we add the aerosol only in the mid-levels, this is only the cold pool effects, essentially. We get a very similar profile with slightly less of an increase in the updraft velocities, 8 to 10%. And then when we only have the invigoration effect when the aerosol is at low levels, we see that increase is further suppressed down to, at most, 3 to 4%. Not a lot. Even in the most extreme case here, we're talking on the order of 10% in these idealized simulations. What about other studies? Paper published in 2018 in Science looked at this from both a modeling perspective as well as an observational perspective to try to quantify the potential influence of aerosols on convective updrafts. The top panels here are showing you results from model simulations. The bottom are from observations. And this is based on Go Amazon observations and some idealized simulations. And in the paper, they suggested that there's evidence for strong anthropogenic invigoration based on both of these results. You can see that here in the top, going from black to red is going from cleaner conditions to more polluted conditions, and you'll see the updraft velocities are going from 2 to 3 meters per second all the way up to 10 to 12 meters per second or so. So instead of a 10% increase, this is an increase of a factor of 4-ish, give or take. On the bottom of the observations, the colors here show you the updraft velocities. So going from cool to warm colors is increase in the velocities. Left to right is increase in the aerosol concentration. And you can look at this and see, well, there's not a lot of reds on the left and there's a lot of reds on the right. So that might indicate that there's a strong increase in the updraft velocities in the more polluted conditions based on these observations. Problem arises in that convective clouds, their updrafts are highly sensitive and exhibit large variability relative to environmental parameters, in particular wind shear and cape. This is a figure that came out of a paper in 2018 where we looked at the parameter space of the slope of updrafts, the width of updrafts, but also this impact of potential warming. This is represented by delta T. So if we look at this plot down here on the bottom left for a squall line scenario, this axis here represents how much warming you might see due to aerosols. We just throw it in the model, see what happens. And then the y-axis is how slopey the updrafts are. And you can then the colors are shown here are the updraft velocities. And you can see that, well, perhaps there's an impact with warming for very upright updrafts. If I go across there, the change in the colors is quite significant. On the bottom, those curves start to level out. So there's this sort of balance between what the actual characteristics of the updrafts are relative to how much warming you might get. One of the things that came out of this work is that in order to actually observe the potential impacts of warming due to the added latent heat release, observations, at least the observational uncertainties or errors currently would limit the ability to actually detect some of these changes, at least without large field campaigns, which I'll get into in a bit. Complicating this further, so I led off with trying to quantify this with a set of idealized model simulations. Those were just a single model simulation, single attempt at this. A better way to do this is to use multiple models, and we'll get into that even more later. But I wanted to show you this here from Peter Marinescu's paper a few years ago in JAZ, where they looked at the sensitivity to aerosol loading, so solid and dashed as low and high aerosol conditions using several different models, which are all the different colors. And you can squint your eye, turn your head sideways, and there's a lot going on here. The take-home message, though, is that in many of the cases here, the difference between the solid lines, which is the intermodal difference, is just as large, if not larger, than the difference between the solid and the dashed, which is the aerosol effect. So trying to tease out what the actual aerosol effect is quite challenging, even once we add in multiple models. So a lot of this led to the work or the development of a paper that was published last year in ACP, led by Adam Warble. Hugh was a co-author on it, myself as well, and I think Wojtek was on that paper as well, where we tried to reevaluate. We should have called it a reevaluation, maybe. It was called a critical evaluation. And we revamped the figure that I started off with from the science paper, from the Rosenfeld et al. Science paper, to what I hope better represents the complexity of the problem, and also adds on this area on the left, which represents the environmental conditions that also play into determining the structure of convective clouds. So things that we're all well aware of that perhaps have been glossed over a bit in some papers: CAPE, wind shear, so on and so on. And then on the right, we have all the different processes, microphysical processes, color-coded based on their impact or the aerosol loading impact on the process. So in this case, as the aerosol increases, condensation increases, but then also how that would impact the updraft speed. So in this case, the arrow's up. That would cause the updrafts to be larger. You'll notice there's a lot of gray in here. That means we're either uncertain or unsure as to how that actually would play out. So in addition to this schematic that I think better represents how complex this problem is, in the summary conclusions of this paper, we also put together a list of what studies moving forward really should focus on. And it was broken into observational studies and modeling studies. In the observational category, we highlighted improved retrievals. This goes down to the uncertainty in the observations, making it challenging to actually statistically pull out some of these effects. Focusing on single convective cloud types, avoid subjective selections, post hoc analysis, control for atmospheric state parameters, apply significance testing, which surprisingly is not often done, and then avoid assuming causation from correlation. So I highlight a few things here from the literature that sort of led us to come up with these conclusions here. So this is a paper from Lee et al. In Nature in 2011. They analyzed observations at the DOE ARM SGP site in Oklahoma. On the x-axis here are binned concentrations of condensation nuclei, and then the y-axis is cloud thickness. If you focus on the blue line, you'll see that there's a basically linear increase here in the cloud thickness or cloud depth as the aerosol increases. And in the paper, this was claimed to be invigoration. I put invigoration in quotes because it came from the paper. So this has to do a bit with claiming causation from correlation. This correlation here, claiming that this is related to those processes is a little bit challenging, just solely based on these observations alone. This was later looked at by Adam Warble in 2018. He analyzed the exact same data set, but added in the background meteorology, the atmospheric state. And so these plots are essentially the same as the top panel here. the CN categories correspond to the same values on the top panel, except the y-axis now is CAPE, and on the right, it's the level of neutral buoyancy. And you'll notice that as the aerosol loading increases, so does CAPE. Well, that's interesting. Why might that be? This is in central Oklahoma. Chances are, if you have a lot of CAPE, your air is coming from the south, and what's to the south is the lovely metropolis of Dallas, and beyond that, you have San Antonio, you have Houston, you have a lot of pollution sources, so you have this influx of warm, moist, unstable air that's also bringing in a lot of junk. So teasing out whether this is meteorology or aerosol related is challenging. Now, I'm using Texas as an example. We're going to come back to that in a minute here. Not a minute, probably 2 minutes. No, it's going to be more than 2 minutes. I forgot what I put in here. Going back to this slide, this figure I had put in here earlier from 2018 paper in Science that demonstrated this increase in updraft velocities as aerosol increases in color. Getting back to the state variable here. In this paper, they demonstrated that the CAPE remained pretty much the same across all these cases. So this increase you see in the velocities, they attributed not to changes in the meteorology. CAPE is shown here in the top in these circles, and that corresponds to the right axis here. Looks pretty similar to me. So I plotted up my own. Does anyone know what this is? I intentionally left labels off of this. Does anyone know what this is a graph of? We got a microphone here I can kick. I was told that I can throw this at someone if they want to answer. No one wants to answer? What's that?
Microsoft Excel.
I did it in Microsoft Excel. This is the only thing I've ever made in Microsoft Excel, right here. Probably would have been faster for me to code it up in Python, but these are CO2 observations on a log scale. Doesn't look like CO2 is really changing. This is how you normally see it, right? CO2 is increasing, right? But if you put it on a log scale, it looks like, CO2 is not really changing. If you look up here, CAPE is on a log scale. Seems a little odd and to me, but joking aside, that it's hard to actually tell if CAPE isn't changing there, given how it's presented, right? So I like to use this CO2 thing as an example of how we can maybe perhaps conceal certain things. Anyway, moving on to modeling studies. In the conclusions of this paper, we wrote out a few suggestions. Improve the representation of updraft dynamics. Perhaps hint to some people in the room. Expand usage of LES, so moving toward higher resolutions. Avoid strong conclusions based on a single simulation. I'm definitely guilty as charged for that, and in fact, I started off talking about simulations of that, using single simulations. Consider the limitations of the modeling framework, in particular using idealized simulations, short-term simulations, and then use objective representative sampling methods, as well as provide some observational context, try to ground things in some sort of truth. So, motivated by that long list of things that we should be doing, recently in 2021 and 2022, we had a dual field campaigns occur, DOE-sponsored Tracer, and then the NSF-sponsored Escape field campaigns. Tracer took place over an entire year, fall 2021 to 2022, deployment of the ARM mobile facility, multiple radars using various new scanning strategies, frequent atmospheric soundings. And again, this was year long, so this is a large data set in a location that experiences convective clouds very regularly. If you've been to the Gulf Coast in the summer, you can pretty much guarantee that you're going to see something on almost any given day. So it seems like an ideal location to go study convective clouds if you want to see a lot of them in a short amount of time, right? And it's also in an area with a very complex aerosol environment. Between just Houston itself, you also have the port of Galveston, lots of aerosol emissions, highly variable spatially. Escape, again, the NSF component. This employed various mobile platforms or mobile radars, 2 aircraft. It was it coincided at least partially with tracers. So we have ground-based observations from the AMF, the ARM mobile facility, but then we also have these co-located, in many cases, airborne observations. Most of the focus of tracer was in the month of June in 2022, when the research flights occurred, and those paths are shown up there if you're interested, and then all the mobile deployments are shown in the bottom. So rather large data set in an area with complex varying aerosols and convective clouds. So this seems like this is a prime opportunity to try to address some of those points that were raised or put forth in the end of the Varble et al. Paper. So let's look at this from an observational perspective. This is work that's being led by Ali Al-Jabri, a PhD student at the University of Oklahoma. This is work that is in prep, is waiting on me to actually go through the paper, which I wanted to do this morning, but just too tired. So what he's done is he's looked primarily at those DOE ARM observations from tracers. So that site is located right there, the black star. This is in the vicinity of the Houston metro area. The Houston NextRad radar is the green star right there. And he's using a variety of observations. There's several meteorological variables that he's using, including SIN, CAPE, LNB, 2 different measures of relative humidity, and then bulk wind shear in the vertical. Aerosol observations, we're just abbreviating them here. If you're interested in exactly where they're coming from, I can answer that at the end. But basically different size ranges of aerosols, and then also aerosol optical depth. We're using data from the NextRad radar, primarily the composite reflectivity, which is used to track cells to get us the area of those cells as well as their the ecotop heights. And then he also is using ERA 5 data to look at the sort of larger scale conditions, in particular pressure patterns and wind. He's focusing primarily on isolated convective cells, so we're trying to ignore things that have grown upscale. So we're throwing out MCSs and things like that. And he's also focusing on early stages of development to really isolate those initial impacts that may be occurring due to changes in aerosol location. And so all of the convective cells that he's identified during the summer period are shown there on the right in the Houston area. Again, it's very common to find convective cells in this area. And then they're color-coded by their ecotop heights, just for reference. So the first thing he did was he set out to look at that covariability problem that I highlighted in 2 papers earlier, where the aerosol and CAPE varied together. CAPE increased as aerosol increased in central Oklahoma. Similar correlation was actually shown in a paper on Relampago and cacti in central Argentina, where they found CAPE increasing with aerosol loading. So we'll look at that here. You maybe you're hypothesizing how that might play out here in Houston, but we'll get to that in a second. So the first thing down here in the bottom right, these are correlations between aerosols. We would hope that they would be relatively well correlated. They are. The only difference is this box right, the only caveat is this box right here. The CN isn't as well correlated. That just has to do with the different size ranges of that instrument capturing small particles that the other variables aren't actually capturing. Meteorology. Shouldn't be a surprise that CAPE and LNB are really strongly correlated. Other things that pop out, SIN is relatively high correlated with CAPE, as well as low-level relative humidity. All the stars here just show that they're statistically significant. That was another bullet point that was put out in the Varble paper. None of that I don't think is super surprising. Where things get interesting is this bottom left corner, where we have the aerosol variables on the y-axis and then some of the meteorological variables on the x-axis, and you don't see very much correlation at all. Why? Well, if we have flow from the south bringing that warm, moist air off the Gulf, that would tend to be bringing some unstable air in. It's bringing what air with it? It's bringing air from over the Gulf. It's not polluted anymore. That causes things to be quite a bit different than the situation that we saw at the SGP site in Oklahoma, where the air from the south is advecting aerosol sources from Dallas, Houston, so on and so on. Now, you might be saying, well, then why are there not a bunch of negatives here? That is something we have not figured out yet. One thing I can say is that when he looks at the data for the entire summer, not just the days where there's convection, you do see negative correlations between CAPE and the aerosol variables. So it is somewhat indicative that on a larger time scale, that is actually what we are seeing. Okay. He looked at individual variables, single variable analysis. So in these plots here, we're looking at the area, basically find the 15 dBz and map out the area of that. And that's shown here on the y-axis. And then the different variables here are binned into quintiles, starting with CAPE, shear, and then CCN on the right. Showing here the median interquartile range, and then like 1.5 times the interquartile range there in the bars. For CAPE, you say, oh, there's a little bit of an increase there, going from the low CAPE to high CAPE condition there. When we look at shear, there's a bit of a stronger increase here with cell area as the shear increases. This was interesting to me, at least, because there's been a lot of modeling and theoretical work that show that cells should be somewhat wider as the shear increases. If you start tilting things, that should widen them. There's been some work on hail that shows that the supercells that form in stronger shear environments have wider hail growth zones, and we're actually seeing that area increasing in these observations. And then if we look at the aerosol variable, I just picked one, CCN here at random, you see the opposite, that the cells actually are narrower or smaller when we have more aerosol, which may seem like it contradicts some of the prior motivation that I was talking about earlier. This was all just single variables. He took it a step further and did a multiple linear regression analysis using wind shear, CAPE, mid-level relative humidity, and the CCN. The stars show you which variables are statistically significant, and then the y-axis is just the standardized coefficient. Shear and the CCN are the two that have a statistically significant relation. So these two right here, statistically significant, CAPE, not so much. And you get a significantly positive effect for shear and negative there for CCN. So he took a closer, I should say that he did go beyond just linear regressions and has additional work using random forests that shows very similar work, or very similar results. So we took a closer look at this CCN cell area relation, which was somewhat intriguing that it was a negative relation. And he plotted up just a scatter plot of the cell area versus the CCN constant. I should say CCN, not CNN. This isn't a news channel, sorry. And this is what you get when you fit a line through it. You can fit a line through anything if you really want, but that's what you get, and you can see it as a negative slope, and you might be saying, well, that's a little interesting. What jumped out to me here is that, well, first of all, negative slope aside, you have no points up there in the upper right. There's no cases here where you have high aerosol conditions, high aerosol loading, and large, wide updrafts. You have these sort of three conditions here where, at low aerosol loading, you might have really wide storms or really narrow ones. And then at high aerosol loadings, you only have narrow convective cells. So the question is this just a correlation here that we're seeing? Is there actually something going on that's causing those cells to be smaller because of the aerosol? So to look at this, I guess I should have. He applied k-means clustering to categorize those different conditions into 3 different clusters, which are shown in the colors up here, blue, green, and black. And then on the bottom, you can see them all distributed out in time to see that more or less these different clusters are occurring at different times of the year. We're not seeing something that's only occurring in June, only occurring in July, so on. They're pretty much spread out over the entire field campaign. Right. So he looked at these in more detail, specifically looking at ERA 5 reanalysis. So he plotted up the surface pressure, mean surface pressure in these different clusters, as well as the winds. And what we see here is in this cluster 3 is that we have this super strong, but a strong high pressure sitting over the central part of the United States. What we're seeing here, the reason that we have these high aerosols is this is actually forcing air south. So at the location of the DOE arm site, we're actually advecting air from the north, in this case, aerosol or pollution sources. And so that's why we're seeing an increase in the aerosol loading in this case. And then these are relatively narrow. We don't have a lot of forcing in these cases. These are just relatively weak, probably mostly associated with just weak sea breezes. If we move to the next one, bottom left here, so these are narrow cells in relatively clean environments. we'll see that that high pressure system is gone, and now we have a low over the far north of the Great Lakes. You'll see we have rather strong onshore flow here that's transporting relatively clean air over the area. And if you look closely, you'll notice that it kind of abruptly stops over Texas. So in this case, we find that on average, there's this sort of convergence, area of convergence that occurs over Texas. And so there's some additional forcing that's actually occurring. Sorry, I lie, wrong one. Take back what I just said, that the arrows continue, so this aerosol is just being essentially piped right up through the central part of the United States. We don't have the large scale, or sorry, the convergence area here, and so we just get still relatively weak, small convective cells. Now, the one that has the wider one. So in this case, this low is now significantly stronger. We still have onshore flow. We have a weaker onshore flow. The Bermuda High out there is actually a bit weaker. And in this case, it's a little hard to see here, and I unfortunately didn't include it, but if you zoom in, you'll actually see that there's an area of convergence on average that's occurring over eastern and southern Texas, and we believe that that added forcing is what's causing the convective cells to be somewhat larger or wider in area in those cases. Okay. So back to the list of bullet points. Did we actually address any of these? I'm not going to improve retrieval, so I crossed that one out. That's not what I'm going to be good at. We isolated single convective cloud types, primarily looking at convection associated with sea breeze, isolated convection. Subjective analysis, we controlled for state parameters. We looked at the different correlations between individual variables. Significance testing, I hope I emphasized that, where every time there was a star, there was significance shown, and then avoid assuming causation from correlation, right? The negative trend in cell area with aerosols, we could have just said that the aerosols were causing it, but in fact, it seems like it's more so that the large-scale synoptic patterns controlling both of those parameters together, and that's why we're seeing that relation. Okay. Moving on to modeling, also focused on these two field campaigns. This is work led by Yishi, who's sitting here in the audience, also has a liking for pumpkins. So she's been working on same field campaigns, but focusing on a modeling perspective. She's created a database now of, I think, about 1,000 1-kilometer simulations that span the escape time period. The simulations are run twice per day, so we're getting away from single simulation idealized modeling work and looking at real simulations spanning many, many cases, as well as with an ensemble approach. So she's applied varying boundary conditions, varying microphysics schemes, boundary layer schemes. And then what I'm going to focus on is this last one here, where she changed the droplet concentration to mimic the impact of aerosols. So she ran all the simulations with 2 different droplet concentrations, 200 and 1,000. You can kind of think of those as clean and polluted. So she looked at the cumulative precipitation, the hourly precipitation, on all of the simulations, so that's what's shown here in the upper left. They're color-coded by which forecast model was doing the forcing, HER, NAM, or GFS. One thing she noticed really quickly was that the HER and the NAM overestimate precipitation, and the GFS drastically underestimates it. So when you remove the GFS, which we're going to look at moving forward, especially because it was affecting the means, we get this result here. So we're only going to focus on the NAM and the HER here. The right plot shows you the same data set, but now it's broken down into the 2 different droplet aerosol conditions. So blue is, we can think of as clean, yellow as the polluted. And you'll notice, if we look at the mean here in yellow, that as I go from yellow to blue, this is going from polluted to clean, that the precipitation is increasing in that case. So the cleaner situation tends to have more precipitation. Granted, we are overestimating, the model is overestimating the mean, is overestimating the observations, which are shown in black. But if we go down here to the bottom right, we can see that that's not necessarily related to the aerosol, but it's actually related to the boundary layer scheme. So when she runs this same ensemble, the whole ensemble with the MYNN boundary layer scheme, you actually, in an average sense, get a really good representation of the observations. When you run it with the YSU scheme, you get this overestimation. When you put that all together, you get the top plot there. All right. So again, clean cases lead to more precipitation. And she showed this further here, trying to get at, statistically, if I actually go back, you say, well, that's just the mean. Look at all those different lines for all the different simulations. How can I tell with confidence, statistically, that that's actually what's going on? So she looked at this in a performance diagram framework here. And in the purpose of this, we're just going to focus on these bias lines here. So basically going from this bottom right up toward the left, you can think of as increasing precipitation, right? And so if I look here at the stars, which represent the clean and polluted cases again, going from orange, yellowish to blue, that's a cleaner case, has more precipitation. So that result holds here. And then she broke it down into the individual days during the field campaign to say whether or not that change is occurring all the time, or is it sometimes it's positive, sometimes it's negative. And if you go from, again, the orange to blue, polluted to clean, in every case you go to the upper left, which would indicate more precipitation, suggesting that this is a rather robust response, at least during this month during the field campaign. So what about the updrafts? So I took those simulations that Yishi put together, and I combined all the times and all the simulations together to create this 6,000 point series, if you will, and basically looked at the domain maximum vertical velocity, which has its own issues. I will be the first to admit that. But as a first stab at this, we looked at the domain maximum, and then we took the difference between the clean and polluted conditions. And you can see at certain times, yeah, the polluted simulation has significantly stronger updrafts, 20, 40 meters per second. And at the same time, there's situations where it's the complete opposite. So sometimes it's larger, sometimes it's smaller, right? And if we look at this in a mean sense, which is shown over here, so now I'm plotting the difference in the mean vertical velocity. That's shown here on the y-axis, and this is just a distribution showing you the median and range. You'll see that, I should say the mean, that it's actually slightly negative. So, and actually 75% of the data are negative. So in a mean sense, the updrafts in the clean conditions are actually somewhat stronger, which is opposite to those invigoration arguments that I started off with. And this actually would be somewhat in line with the precipitation being higher for the cleaner case. Again, which is opposite to what we had just showed. So, going back to the list of bullet points from the Varble et al. Paper, were we able to address some of these? Not going to be the one that's improving the representation of updraft dynamics. I completely agree that we need to expand the usage of LES. Running 1,000 simulations of deep convection over a 24-hour period is a little bit expensive, so we weren't able to get down to those grid spacings here, but hopefully in the future we can. We were making conclusions not on a single simulation. These were based on as many as 1,000 simulations. Limitations of the modeling framework, I already highlighted one of those, is the grid spacing in this case, as well as we noticed that one of the issues we had was with the large-scale forcing with the GFS, which was causing some significant underestimation of the precipitation. Objective representation, I didn't cherry pick or anything. I just took the max and plotted a time series and looked at the distributions of that. There was no selecting anything involved in that. And then provide observational context. Those simulations, at least in this case, we looked at the precipitation data to confirm that we were getting something realistic with those simulations. All right, so in summary, we started off with looking at theoretical evidence for how aerosols could influence convective cloud dynamics. We showed through some idealized simulations that cold pool effects may outweigh other impacts, in particular the invigoration effects. We looked at a large data set from recent field campaigns to show that observational evidence suggests that the convective clouds forming in the polluted environment in the Houston area are narrower. I didn't have time to show this, but he also shown that the ecotop heights tend to be slightly lower when the aerosol is higher. However, we think that this is largely related to the synoptic scale conditions that are causing the aerosol and the environmental, the meteorology, the local thermodynamics to change at the same time. And then we also looked at ensemble simulations and revealed statistically significant reduction in precipitation as well as slightly weaker updrafts across a field campaign period from 2022. And so with that, I will stop and take any questions. All right, who do I get to throw this at first? Oh, you get to throw it.
So we have a new, is this on? Can you hear me? We have a new way of using the microphone here. It's tossable. So I'll stand back here and just.
I don't think you get to ask your question if you drop it.
Very, very interesting. From a non-microphysicist perspective, you're saying that cleaner conditions produce more precipitation, but if it's purely clean, you have no precipitation. Isn't that true?
Yes. So this is something that I've spent some time thinking about, because in the extreme, yes, the aerosol, if we didn't have the aerosol, we wouldn't have the precipitation, we wouldn't have that, right? So in the extreme, yes, the aerosol is the most important aspect. I mean, you could maybe make that claim. It's the most important aspect in getting that to happen. But we don't have that purely clean condition on Earth. So we're looking at relative changes to what we expect to see in conditions in our atmosphere.
And just another quick question. Back in the 70s, the impact on microphysics was often diagnosed via precipitation efficiency from the storms. Is that still a potentially useful way of looking at these results?
Yeah, I actually did that. I was working on some stuff with Graham when I was at NOAA, looking at precipitation efficiency from simulations of clouds of TWP ice that maybe I should go back to 10 years later and look at. But yes, that's something that could be looked at in these simulations. Yep. And I think Dan had a question in the back. Oh, man.
Nice talk, Zach. Could you explain, I actually had two questions, if I may. Could you explain what you meant by improved representation of updraft dynamics? I think I know what you mean, but I'm not sure.
Hugh, did you put that in there?
I don't remember.
There's a reason why I crossed it off, because I don't remember.
Maybe it was, well, it's probably pretty close to related to using LES.
Yeah.
Resolving.
I'm wondering if it was in reference to, like, yeah, I think it might be just in reference to grid scale. I don't know if it was reference to like larger scale climate scales simulations where we use convective. I don't remember.
Yeah, I was
I should
wondering if
call
you meant
Adam
like
and
these single column model tests where you just lift parcels. Is that what you mean? Like,
No, that I'm pretty confident of.
okay.
Yeah, I think it's probably grid space.
Yeah.
Getting away from, the big, like, bloom light updrafts.
Yeah.
One longer model.
Okay, I'll read Adam's paper. So maybe yeah, and so my other question was kind of related. Maybe you should expand, or I'm sorry, eliminate the phrasing expand usage of LES and change it to eliminate usage of non-in-training kilometer scale simulations. And that reads me, my real question is, in those early slides you showed, how does the mid-level aerosols that actually did affect the cloud results when the boundary layer did not, how did they get into the cloud? Because if there's no entrainment, how do they affect the cloud?
Yeah, so I don't have that slide in here, but so those simulations, they're relatively coarse. They're not LES. So what we looked at, in that paper, we put in tracers, just passive tracers in the two levels, the two different areas. And in the low-level case, those were obviously being brought into the updraft, but that updraft wasn't really mixing much with the surrounding. Those were squall line simulations, so you can imagine you have these sort of updrafts going off left and right. So that low-level aerosol was just affecting the updrafts and then everything in the upper parts of the anvil. And then where there wasn't really strong updrafts, you could sort of mid-level ascent, especially in the rear end of the storm. That's where it was affecting those storms. So it was affecting more of the trailing stratiform area, precipitation falling out there than it was the actual updrafts itself. Does that answer your question?
I'll talk to you tomorrow morning about it.
Okay, we can talk tomorrow. Yeah. Dan had a question.
Maybe right behind George.
Oh, yeah.
Thank you for the great talk. I'm not an aerosol person, so my question could be stupid. Just a disclaimer. So we know that there are different kinds of aerosols. So when we talk about aerosols, there could be carbonaceous aerosols, sulfate aerosols. by any chance, have you looked into different kind of aerosols? Because when it comes to aerosol precipitation process, their influence is pretty different.
Yeah, I actually had a slide for a prior version of this that was really much shorter, where I had a bunch of chemical species flying around, and then I put them all in like a whirlwind and then just made it a dot, because I was trying to simplify things as much as possible. So we're trying to remove that sort of variability that could be going on. There's been some papers that have looked at the sensitivity to the type, but it tends to be significantly smaller of an impact or less of an impact than changes in the number and size. Did we finally get back to Dan?
Yeah.
I thought you were gonna like jump and hit the ceiling.
No, this is really cool stuff. I was just curious, on the summary slide there, you had two interesting kind of conclusions at the end. I'm wondering if, the two on the right, I'm wondering if there might be something, those might be related. Like, I'm wondering if, like in the case where you found that the convective clouds forming the polluted environments are narrow, which you think are due to the larger scale conditions, is a correlation, not a causation, right? Is that what I'm getting from that? And then you have significant reduction in precipitation in polluted conditions. Are those two related? Could it be simply that the types of storms that are forming they're too weak and narrow in those polluted conditions, so that's why you're not seeing what your original invigoration hypothesis would have shown?
It's possible. The only thing I will say is that in this case, for the same environment, the simulations are run with polluted and clean conditions.
Okay.
And you still see that reduction.
Do you see the same structure in the storms though, when in those?
That is a very good question that I don't have the answer to.
Okay, thanks.
Yeah, you mean between the clean and the polluted? The only thing that I've looked at so far is just the updraft statistics that I showed here. In terms of structure, you mean the area of those cells themselves? Yeah.
The storms look like.
Yeah, so I think that was something that Yishi actually may have some slides on. So Yishi did repeat the sort of the cell tracking that was done for the observations. She did some of that for the model simulations and looked at the area, lifetime, things like that, but that's still very much a work in progress, and I'm not gonna put you on the spot to tell me which way or the other it goes, but that's something that she's looking into.
Yeah, thanks for the talk. I have a question about your observational study earlier part. When you showed the scatter plot between CCN concentrations and convective cell area, like I was wondering about those two variables relationships in terms of like a spatial and temporal relationship. Like for example, if you have a very big cell having a big cell area, but if it's precipitating below, like aerosol concentration should be low. So I think aerosol concentration on x-axis should be what's ingested into the cloud when it's developing, right?
Yeah. So Ali got this exact same question last week from one of his, not the exact question, but a question very similar he got in his committee meeting about how sure can you be that the aerosol is actually what's being ingested into the storms. I think the short answer is we really can't, because if I go back to this slide quickly, nope, that's the wrong one. Nope, that's the right one. Sorry. Right, the aerosol is being measured down here, right, and all the cells are to the north. We can't be guaranteed that that's actually what's going into the clouds. At the same time, it's really hard to have aerosol measurements below each of those clouds. So the way I've argued it is with the data that we have, I think that's the best we can do. I will say that he is restricting the analysis to only looking at aerosol observations. I think it's within 1 or 2 hours before a convective cell. So he's not looking at times after. And then the same with the soundings. He isolates them down to like plus or minus an hour from when the cell occurs. So we're not looking at like a 6Z sounding and then a storm that's at 14Z or something. So, and because of all of those restrictions to make sure that we're, I think, doing the best we can with the data, that's why you only have, and it's still a lot of points, but it's really still not a lot. It's only 100 or so data points that you end up with when you start teasing things down like that. But it's a really good point.
Thank you.
Let's do one more.
And I should say that Greg Farquhar has some students at OU that are looking at this from the airborne radar, so they have a better idea of what's the aerosol that's actually, did I say airborne radar? I meant airborne observations. The aerosol that's actually in the clouds, what the cloud droplet concentrations are. That's a whole nother topic.
I'm talking to this thing. So early on in your slide, you showed a slide where the polluted case had more ice than the non-polluted case. Is that what you meant to say?
This one?
Yeah, I think that might be it. But in the cleaner case, you have larger droplets, which tend to be more likely to produce ice, and they also tend to produce more ice multiplication. And so, can you explain?
Yeah, I went over this a little bit faster than I had wanted. Absolutely. So the idea behind some of this sort of thought experiment comes from the science paper, and so I was trying to follow what the pathway was that they presented in that paper, and the key difference at this stage was that the clean condition produced these raindrops that they said would fall out. So you would remove that mass. So even though they're larger, you have less mass up here, so that you just don't have the freezing that you would otherwise. I would argue that that's probably an unrealistic assumption in these strong convective cells, because these raindrops at maximum are falling on a few meters per second. So if your updraft is 20 meters per second, they aren't going to care if they're this big or that big, they're still going to go up. So I would argue that this assumption is not very valid, and that actually most things would still go up. And then that leads into your point that yes, then size does come into play when it comes to freezing, at what temperature they freeze. And I think that's something that I think that's something that we may have mentioned in one of the papers from 10 years ago, that about this size difference that could come into play here. Yeah.
It seems like ice phase is really critical to this whole thing.
It is.
Absolutely. Thank you.
All right, let's thank Zach one more time.